Hi, good morning. We're going to move forward in Unit 3. We look at topic 3.9, and that is separating mixtures. We're going to focus on chromatography and distillation. Okay, I'm going to share my screen and go there, go there. Let's share this. All right, separating mixtures, pretty easy. Let's see. So separating mixtures. First of all, mixtures physically combined, therefore can be physically separated, right? We often use filtration, and that is based on particle size, right? But filtration will not often work. So we could use a process called distillation, okay? And that separates mixtures based on differences in boiling points. So you would need to have you imagine two liquids mixed together, and they've got very different boiling points. All right. So what would we do? Let's see. Let's set up this little scenario here. I actually did this in high school. Let's put a liquid here, and let's put another liquid here. All right. And they're mixed together, and we need to get them separated. So let's kind of mix those like that. All right. We'll kind of mix them. You see how they're all kind of mixed up now. So what we could do is, if we had the proper materials, we could, with a little rubber tube here, we could put something in here called a condensing apparatus. And there would be a lot going on. There's a tube in here with like cold water in it. You literally connect it to the water at the lab bench, and you let water come through it. And anyway, we would have some heat here, maybe a Bunsen burner or a hot plate or something. And, I don't, we could maybe incorporate those. No, 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 no. That's my daughter. I have to get that later. Let me get rid of this little picture here. Sorry. And this would we can just keep it simple. Come over here. All right. Keep it real simple. But whatever, this is a condensing / condensing apparatus. Okay, just think about it. We're going to start adding heat. We've got two liquids in here, right? So we've got a mixture of liquids. We're going to start adding heat, right? And what we're going to see is, as we add heat, right? No. As we add heat, right, the temperature is going to start to increase of the entire substance, the entire mixture. The temperature is going to start to increase. Well, once we get to the boiling point of one of these liquids, whichever has the lowest boiling point, it is going to start to boil and turn into the gaseous phase. So that will be the liquid with the lowest boiling point. Notice that while that liquid is boiling, the temperature will stop changing. We'll talk about that later, I hope. So let's assume that's the blue liquid here. So what we would see is the blue start to come up through here in its gaseous phase. It will cool and condense and then fall back down here as a liquid. We will no longer, if I can do this, have the blue in here, right? We will just have the green. That was ugly. We will just have the green, and we will have separated that mixture. Wrong color green, not a big deal. All right, we will have separated that mixture. We could then, remove this and put another empty flask, continue heating, and then we could evaporate that, right? This would be the liquid with the highest boiling point. And we could continue to do this until we had separated all of the mixture into the various components, and we did that based on boiling points. Let me know if you have any questions. Okay, the next thing you need to be familiar with in terms of separating mixtures is chromatography, all right? So once again, we can't use filtration. We don't have particles that are of different sizes, so we can't filter them out. Maybe we don't have particles that are have different boiling points. Maybe they are not even in that liquid phase. So chromatography separates not based on size or boiling point, but based on intermolecular forces. Simple as that. All right. So let's talk about how it looks. And this is what AP likes to focus on, chromatography. And it's cool and it's simple. So what we would do, guys, is we would have, this is called paper chromatography. I'm going to get a piece of paper. So it doesn't really need to have a circle up here. It's just a strip of paper. All right. On this strip of paper, if you were, say, in the classroom, we would draw a line on here, okay? And let's just make up some scenarios. We have various colors of ink, all right? This is literally, you could go and get some expo markers. It works all right. You can see what's going on. You can even get black too, all right? Well, we take, and we want to separate these colors to see, we want to separate these dyes to see what colors are in them. That's one scenario. So, and I'm just going, so what I would do is I would put a dot, a really small dot of each dye on the line, all right? It's much smaller than is represented here. A really small dot, okay? Now, I would then take that piece of paper and I would put it in, let's see how good my drawing skills are, a beaker, all right? Or something like that. And in that beaker would be a liquid, all right? Okay, hopefully I can do this well. Let's make our liquid light gray. Okay. Now, what we have here is the chromatography paper. Chromatography paper, right? What we have here are the inks to be separated. And what we have here is the solvent, okay? Right now, currently, this right here is my initial solvent front, all right? That's where it starts. Well, what's going to happen is this solvent, the solvent is going to move up the paper, okay? Just think about moving up the paper. Adhesion, cohesive forces. Adhesive, cohesive forces is going to move up the paper. It's going to pull itself up the paper. Now, I'm just going to make a fake scenario. So we now have our final solvent front here, all right? It's as high as it went. All right. Now, what we can make up, all right, like I said, and just creating a scenario, we could say that this, ooh, that's the wrong color. I don't know what color it is. Let's say that the purple moved to here. And yes, it would probably be different colors, but I'm not going to worry about it. Let's say the blue moved to here. Let's say that the green moved to here. And let's say that the black really didn't even move, okay? So what I now notice is that the blue moved the furthest. And I'm going to write with the solvent. All right. What that means to me is that therefore it was most attracted to the solvent. Remember, chromatography has to do with attractive forces. Those are IMFs. All right. The black moved the least with the solvent. All right. Therefore, it was least attracted to the solvent and most attracted to the paper, right? And we could say that this one was least attracted to the paper. So whichever substance moves up furthest with the solvent is most attracted to the solvent. Whoever stays below is most attracted to the paper. Okay, and vice versa. If you have a question about that, you should ask. Now, we need some more information. What we would be supplied with is we could say that the paper is nonpolar. It could be polar. You would be told, okay? And the final solvent front will say that the solvent itself is polar. It could be vice versa. They're usually opposites, right? So I could easily infer, so we'll make a question out of this, which component is the most polar? And by component, I mean the three dots, the three colors that are represented here. All right. And what I would see is it would be the blue, right? The blue will be the most polar and the black will be the least polar. All right, let me get my pen here. Most polar, least polar. Most polar because it was most attracted to the polar solvent and less attracted to the nonpolar paper. This is the least polar because it was the least attracted to nonpolar solvent and most attracted to the paper. All right, and we know that polar substances attract polar substances, right? We know that the dipoles of each will attract each other. So that's what we're applying here, and most attracted to nonpolar paper, right? And we'll look at some examples, further examples of this, okay? That's really it. I mean, that is really it. Separating mixtures, filtration, particle size, distillation, boiling points, and then chromatography based on intermolecular forces, okay? May have a little lab we can do with this. All right, but I'm gonna go ahead and end that there. Awesome.